Hello everyone, welcome to online classes for DPS Siliguri. Myself Shomnath sir, and today we discuss about the topic electric flux and Gauss's theorem. This is the second lecture for electric flux and Gauss's theorem, and overall it's my third lecture. And today we discuss a very important topic, that is electric field due to uniformly charged thin spherical shell. Electric field due to uniformly charged thin spherical shell. So first we imagine a thin spherical shell. Let the radius of the shell is r and q charge is uniformly distributed. Q charge is uniformly distributed throughout the cell, and we have to find out electric field in three positions. We can find out the electric field in three positions. Number one, outside the cell. Number two, on the surface of the cell. Number three, inside the cell. So we have to find out number one, electric field at small r greater than capital R, means outside the cell. Number two, electric field at small r equals to capital R on the surface of the cell. And number three, electric field at smaller less than capital R, means inside the cell, which is very important. Very important. So listen carefully. It's a very important topic for board exam. So you can say it's a coming soon topic. So first we discuss about the first one. P is a point which is at a distance small r. This is the case 1 where small r greater than capital R. So we have to find the electric field at point P, which is at a distance small r from the center, and the small r is greater than capital R, means outside the cell. So for that we imagine an imaginary Gaussian surface. So why we imagine a spherical Gaussian surface? Because this one is a spherical shell. Now we know from the definition of electric field, for positive charge the direction of electric field is outside. So this one is our electric field, and we also know that area vector, which is normal to the surface, and this is also outside. So first, if you consider here also, both are in the same direction. If you suppose this side also, area vector and electric field, they are in the same direction. So the first important thing is electric field and area vector, they make an angle 0 degree. Now from the definition of electric flux and Gauss's theorem, what we can write? We can write electric flux, that is equals to integration of E dot ds, that is equals to 1 by epsilon naught charge enclosed by the surface. Now from this part, electric field and area vector are in the same direction, so we write E ds cos 0 degree, that is equals to 1 by epsilon naught, and this imaginary Gaussian surface encloses how much amount of charge? Q amount of charge. So in place of Q enclosed, we can write Q. Now that is equals to E ds, because cos 0 is 1, equals to 1 by epsilon naught Q E ds, that is Q by epsilon naught, and the surface area of that imaginary Gaussian surface, which is a spherical, which is also spherical, is 4 pi r square Q by epsilon naught. From this, what we can say, E equals to 1 by 4 pi epsilon naught Q by r square, and a very important thing, E is inversely proportional to R square. That means here electric field is non-uniform. This one is the case 1. Now case 2, if we consider the point P, if we consider the point P which is if we consider the point P which is on the surface. So now we consider the point P on the surface. So this one is our smaller. So area vector normal to the surface, and electric field is also in the same direction. So now this is the second figure. So here we can write case 2, and here we can write smaller equals to capital R. So in the first one, smaller greater than capital R means outside the cell. Now in the second one, smaller is equals to capital R means on the surface of the cell. So when the on the surface of the cell, again you can write from the definition of electric flux, and from Gauss's law we can write flux. Electric flux is E dot ds, that is 1 by epsilon naught q enclosed. This line is also the same because the angle is 0 degree. This one is how much charge enclosed by this, the q amount of charge enclosed, so this line is also same. Now this one is E dot ds is this, but now in the last line what happened, here the radius is, here the smaller is equals to capital R. So what you can write, 4 pi capital R square, that is q by epsilon naught, which means E equals to 1 by 4 pi epsilon naught q by R square. That means it is constant. Now the third one, this is the second one. Now the third one, when case 3, smaller inside the surface means smaller less than capital R. So now what happened? Electric field will remain same, but the point is inside. As the point is inside, now we imagine a Gaussian surface, imaginary Gaussian surface within the shell. So again we can write from the definition of electric flux and Gauss's law. Electric flux is E dot ds, that is 1 by epsilon naught q enclosed. Now again if we consider the area vector ds, electric field and area vector are in the same direction. So E ds cos 0, that is 1 by epsilon naught. But now inside this cell the amount of charge is 0 because it is on the surface. So inside the cell electric charge is 0. So as the charge is 0, we can write 1 by epsilon naught into 0. So E into ds equals to 0. So E ds is 0. E into 4 pi r square is 0. So basically E is 0. So we have 3 points, one outside the cell, number 2 on the surface of the cell, number 3 inside the cell. So what we find outside the cell, value of electric field 1 by 4 pi epsilon naught q by r square. On the surface 1 by 4 pi epsilon q by capital R square, which is fixed, and inside the cell which is 0. So from that we can draw a graph, smaller equals to capital R. It's on the surface, it will be increased, and then this is on the surface 1 by 4 pi epsilon naught q by r square electric field, and it's outside the cell and it is inside the cell. Its overall R outside the cell in electric field is inversely proportional to r square. So the graph is hyperbolic. Inside it is 0 and on the surface it is maximum. This one is for the shell. But sometime in entrance exam or in sometime in board exam also, in objective type question. In place of that spherical shell, they can use metallic sphere. Remember, they can use metallic sphere because spherical shell is in your syllabus, sphere is not in your syllabus, but examiner can use metallic sphere. If they use metallic sphere, so see what happened, everything is seen as it is metal. As it is metal, we know inside the metal electric field is 0. So whatever be the charge, that is only on the outer surface. So everything is same, even figure is also same, but the figure is little bit different. How it is little bit different? How it is little bit different? I just want to explain you. This is smaller equals to capital. This is smaller greater than capital, less than capital. This is E. Everything is same. Here you have a continuous line, but here you have a discontinuous line. Why it is discontinuous in case of metal and why in case of shell it is continuous? As it is a thin shell, so that, and especially it is a non-metallic. Thin shell means it must have some thickness. As it must have some thickness, the charge is on the surface. I'm talking about thin shell. For thin shell, it is on the surface. And as it is on the surface, so charge present outside as well as inside. That means it must have some thickness, although the value is very, very less. So it is a continuous line. But here, as it is a metal and it's a solid, so no charge inside, the charges are only on the outer side. So it is starting from the outer edge. So you can say here at the point this, it is discontinuous. Okay. So after that, next very, very important, we proof Gauss's theorem by using electric flux. The last one we prove Coulomb's law by using Gauss's theorem. Now we just reverse it. We have to prove Gauss's theorem with the help of Coulomb's law as well as electric flux. So next, Q is a point charge and P is a point which is at a distance r, and if we imagine an imaginary Gaussian surface whose radius is r, area vector normal to the surface, and electric field is outward. Electric field is outward. Electric field is outward. So what is the angle between electric field and area vector? Electric field and area vector is 0 degree. Now from the definition of electric flux, we know that is the integration of E dot ds. As they are 0 degree angle, so we can write E ds cos 0 degree, that is E ds. So E into ds, what is the surface area of this imaginary Gaussian surface? We repeatedly say it imaginary Gaussian surface because that is an imaginary surface and first given by Gauss. You can say it also because you are proving here Gauss's law. So if you want, you can not use that imaginary Gaussian surface. You just say it the imaginary spherical surface also. So E into 4 pi r square. Let it be equation number 1. Now from Coulomb's law, we know electric field due to a Q charge at point P, which is at a distance r, is 1 by 4 pi epsilon naught Q by r square. If we put this value here, so electric flux is 1 by 4 pi epsilon naught Q by r square into 4 pi r square. So 4 pi r square cancel, Q by epsilon naught. So we proved Gauss's theorem. So these are simply reversing. If we prove Coulomb's law, we use Gauss's theorem or Gauss's law. If we prove Gauss's law, we use Coulomb's law. Hope you understand this one. It's a very simple thing. Now, related to this electric flux and Gauss's theorem, Gauss's law, now we want to discuss some numerical which are very, very important for board exam, I repeat, as well as for entrance exam. So my first question is, it's a very simple question, but so many students confused with that question. What is the question? Question is that a dipole is there. What do you mean by dipole? Plus charge and minus charge. A dipole is there, suppose separated by distance 2L. So they give you a dipole whose dipole moment is suppose 2 microcoulomb meter. So they don't give you the length and all, they don't give you the charge, they just mention you a dipole whose dipole moment is 2 microcoulomb meter, which is enclosed by a spherical Gaussian surface, whose radius is 2 meter. So it's a very simple question. A dipole whose dipole moment is 2 microcoulomb meter and enclosed by a spherical Gaussian surface whose radius is 2 meter. The question is, find the flux, electric flux enclosed by the surface. So don't confuse, it's a simple question. They give you this data to confuse you. The simple answer is, as you have to find out the electric flux from Gauss's theorem, 1 by epsilon naught into charge enclosed by the Gaussian surface. And here, how much charge enclosed by the Gaussian surface? As you have a dipole, so you have plus q as well as minus q. So plus q plus minus q, the answer is 0. So total charge enclosed by the Gaussian surface is 0. So your flux is 1 by epsilon naught into 0, the answer is 0. Okay, this is the first question. One more. My next question is, Q charge is placed at the center of a metal whose inner metallic sphere whose inner radius is A and outer radius is B. Within that portion is cavity, or you can say air. Find the electric field at point P, find the electric field at point Q, find the electric field at point R, which are at a distance R1, R2 and R3 from the center. Okay, and as well as they can ask you, suppose we can imagine a spherical Gaussian surface. So what is the flux for that Gaussian surface? They can ask you. This one is one more spherical Gaussian surface, so they can ask you flux 2 or phi 2, and this one is another Gaussian surface, so they can ask you flux 3. So I repeat the question. Q charge is given at the center, point charge Q is given at the center, which is enclosed by a metallic sphere whose inner radius is A and outer radius is B. In between the space is given a cavity or air. Question is that find the electric field at P, find the electric field at Q, find the electric field at R, which are at a position R1, R2 and R3 from the center, as well as find the electric flux by the Gaussian surface. Phi 1, find the electric flux by the Gaussian surface, this R2 whose radius is R2, and also find the electric flux on the Gaussian surface R3. And you don't believe, this question is very, very important. I think 5 to 6 times this question asked in board exam as well as in entrance exam. So this one is a very, very important question, and the answer is very simple answer. So let's try how to solve this question. First of all, as this is a Q charge, if we suppose this is a positively Q charge and in the metal you have ocean of free electrons. So this Q charge is attracted by the free electrons. So what happens? The negative charge induced here, and the value of this negative charge is minus Q. And as all the electrons, free electrons, are moving in that side, so this side is the deficiency of the electron. So this side is positively charged, deficiency of the electron, positively charged. So let it be plus Q. This one is plus Q, this one is minus Q, this one is plus Q. Now net charge on the metal is 0, and as the net charge in the metal is 0, directly you can say inside the metal no electric field is there, but we have to solve it by using Gauss's theorem. So first, if you want to find out the flux for this phi1, what we write? Flux phi1, that is 1 by epsilon naught into charge enclosed by that surface. How much charge enclosed by that surface? This thing. So we write the flux is this one. So this one is our first thing. Now this one is equals to integration of E into ds. E is the electric field at point P and ds is the surface area. Both are in the same direction, so angle is 0. So you can directly write E at P. You can directly write E at P into ds, and it's a spherical surface. So what is the surface area? E into 4 pi r, the radius is 1, r1 square. So from this, what about EP? EP is 1 by 4 pi epsilon naught q by r1 square. So you find out electric flux 1, you find out electric field 1, the first one. Now the second one. Second one is this one. So for this one, how much charge enclosed? Flux phi 2, that is 1 by epsilon naught. How much charge enclosed? See, within this one, this is plus Q and this is minus Q. So what you can write? Plus Q plus minus Q. We can put it in second bracket, that is equals to 0. So electric flux for the second one, because we put it here second, so electric flux for the second one is 0. Now as the flux is 0, from the definition of electric flux, we can say electric field at 2 into ds. So electric field at 2 into ds. And now in this one, the radius is r2. So what we can write? E2 into 4 pi r2 square. But as the flux is 0, so electric field is also 0. So now you solve the second one also, and the third one. For that, suppose we remove the first one. For the third one, flux 3. For flux 3, if you see here, according to Gauss's theorem, 1 by epsilon naught into charge enclosed by, now that Gaussian surface, plus Q minus Q plus Q. So what you have? Plus Q minus Q plus Q. So what you have? Q by epsilon naught. So your flux is Q by epsilon naught. And what is the electric field at point R? Okay, electric field at point R. Integration of electric field at R ds, angle is 0 degree. So electric field at R into integration of ds, integration of ds, surface area, spherical surface. So ER into 4 pi R3 square. So electric field at R is 1 by 4 pi epsilon naught Q by R3 square. So now you find out flux as well as electric field. So you understand it's a very, very important numerical and very, very conceptual numerical, and this type of question asked in board exam as well as in entrance exam, even in your school exam, anyone can ask you this type of question. Now the next question is very important. Next question is very important from NCERT book. I mentioned you the question number. Example 1.11 is the question number. Here what is happened? You have I coordinate, J coordinate and K coordinate, means x axis, y axis and z axis. This one is the origin and a cube is put here. A cube is put here. Cube is put here. Whose length, breadth and height is A, and which is at a distance A from the center. So from here to here, that distance is A, that distance is A, and it's a cube. So it's from each edge is A. And now electric field is given. Electric field is given, its value is alpha root under x I cap, and it is also given the value of alpha is 800 Newton per centimeter to the power half. A is given 0.1 meter or 10 centimeter, and question is find number 1 total flux, find number 1 total flux, number 2 find number 1 total flux, number 2 total charge within that enclosed Gaussian surface. Yeah, total charge within that Gaussian surface. This one is your question. So before we start this question, see, it's a very important question. Here x is given. What do you mean by x? X is the distance for this one, because this I means x axis, y means j means y axis, and z means k axis. Now if we imagine this cube, like, if you imagine this, like, although it's not a cube, it's a cuboid. If you imagine like this, so what happened? How, if you put it like this, how many surfaces you have? 6 surfaces. This is 1 surface. This is 2, 3, 4, 5, 6. So for this, this one is 1 surface. This one is 2nd surface. This one is 3rd surface. This one is 4th surface. This one is 5th surface. This one is 6th surface. If you see it properly, except these two, with all these 4 surface, electric field makes an angle 90 degree. Why? Because the direction of electric field is I cap, means your electric field is given in that direction. As the electric field is given in that direction, so electric field and the area vector for 1, 2, 3 and 4, this force side means, if you consider this one, so except these 2 surface, front, back, top and this, in all this, with all this, if that red one is your electric field, see, electric field makes an angle 90 degree, electric field makes an angle 90 degree, electric field makes an angle 90 degree, electric field makes an angle 90 degree. And we know, as the electric field and area vector makes an angle 90 degree, so your electric flux is 0. So for this 4 part, electric flux is 0. So you have only 2 parts, this one and this one. So let this one is the first part and this one is the second part. So if we consider the first part, here electric field is fixed. So what is the distance from here to here? A. So your electric field is how much? Let it be the first one, because from here to here the electric field apply in that position, because here electric field is alpha into root x. That means it depends on distance. That means it is a non-uniform electric field. So the value is alpha into root under A. Later on we put the values. This distance is A and the direction is I. Now if we consider the area vector of this one as it is in this direction, so area vector, let it be ds1 or ds1, that is the area is a square, so a square, and what is the direction in this direction? Means minus I. So your flux, this one we suppose here, okay, suppose this one is 1 and this one is 2, because we first mentioned it here 1. So flux 1, that is electric field 1 dot area vector 1, it's a dot product. So how much you have? Alpha root under ai dot a square minus I, and we know I dot I is 1, and here you have minus, so your answer is alpha a into a square. This is your first flux. Now if we consider for this one, second one, so electric field 2, that is alpha into, from this position to this position, if you consider the distance, this one is A, this one is A, so this one is 2A. So what we write? 2A, electric field is the same direction I, and in that portion and in that portion, area vector in this direction, area vector in this direction. So if we consider the whole area is S2, that is area is S2 and the direction is I. Now from this, your flux phi 2 is E2 dot S2. See, as we consider the whole area, so we are not using integration. So that is equals to alpha root 2a I dot a square I. So what you have? Alpha root 2a a square I dot I is 1. So you have this two flux, flux 1 and flux 2. So what about your total flux? So what about your total flux? Total flux is flux 1 plus flux 2. Now see, flux 1 is how much? Minus alpha root a square, and flux 2 is how much? Alpha root 2a square. Obviously that part is higher part, so we can take the common part, a into a square root 2 minus 1. Now we can put the values. So alpha is 800, a is 0.1 into 0.1 square, root 2 is 1.41 minus 1. After solving this, we get the value is approximately 1.037 Newton meter square per coulomb. Now, when you get this one, flux, that is the first question, find the total flux. After finding the total flux, the second question is how much charge enclosed by this. So, total flux, that is equals to 1 by epsilon naught charge enclosed. So, charge enclosed is epsilon naught into total flux. That is, total flux is how much? Epsilon naught. 8.854 into 10 to the power minus 12 into 1.037, and it is approximately 9.184 into 10 to the power 12, 9.184 picofarad. The unit is in coulomb, unit is in coulomb, so pico coulomb. Now I want to discuss some FAQ question, frequently asked question related to that electric flux and Gauss's theorem. So see, suppose you have a imaginary Gaussian surface which is cubical Gaussian surface, and see from a simple cubical Gaussian surface how many type of question they can ask you. First question, they put a charge Q at the center and they ask you what is the electric flux through that Gaussian surface. So your answer is very simple and very prompt. The answer is 1 by epsilon naught into Q. Very simple, we all know, because that cubical Gaussian surface enclosed by Q charge. Now the second question, they can ask find the flux through each surface. So now how many surfaces you have? 6 surfaces you have. So through each surface 1 by 6 Q by epsilon naught. Okay, now they change the type of question. Now they put the charge at the corner. Now they put the charge at the corner and ask you what is the flux through the Gaussian surface. So we know from solid chemistry as well as from this one, this type of situation is the body centered Q, and if the total charge is Q, so this portion contribution is Q by 8, because it's the 1/8 part is contributed here. So your flux is how much? Your flux is 1 by epsilon naught into Q enclosed, and now Q enclosed is Q by 8 by epsilon naught, that is 1 by 8 Q by epsilon naught. Now they ask you one more question. Find the flux through each connecting surface. So how many connecting surfaces you have? 3. So flux through each connecting surface that is 1/3 of this, that is 1/3 of 1 by 8 Q by epsilon naught, that is 1 by 24 Q by epsilon naught. Now they ask you one more type of question. They can put you. They can put the charge particle at the edge. So if they put the charge at the edge, then from again solids chemistry or solid structure, you know that the contribution is Q by 4. Means if you have a beam and that beam is connected with the 4 room, or if you have a pillar, the pillar is connected with 4 rooms. So electric flux is 1 by epsilon naught. How much charge enclosed? 1 by epsilon naught into Q by 4. So your answer is Q by epsilon naught. After that, they can ask you how much flux through the connecting phase. So when you have a beam, means a beam connected 2 walls. So connecting phase, 2 connecting phases there. Flux through each connecting phase is half of this one. So what you have? 1 by 4 Q by epsilon naught, that is 1 by 8 Q by epsilon naught. The next one is they can put the charge particle here, means on the wall means on the side. So in that case, half is inside, half is outside. You all know that. So electric flux is 1 by epsilon naught Q enclosed, that is 1 by epsilon naught Q by 2, that is Q by 2 epsilon naught. Q by 2 epsilon naught, and as you have only one phase, so in that case, no this type of question is there, flux through the connecting phase. As you have one connecting phase, so the answer is same. So after this, today I conclude my lecture here, and I think we almost cover all the things related with the electric flux and Gauss's theorem. So that is my third lecture. Today I conclude that lecture. In next lecture Means in the fourth lecture, we start with the electric potential energy, work done, and then find electric potential due to electric dipole at axial position, at equatorial position. This all things are remain. So and obviously related to that, we give some assignments also. Try to solve this assignment and send it to the respective teacher given in the list. Up to for until then, bye bye, and stay at home. Bye bye.